Swayam Prabha. Digital India. Educated India.
Good morning everybody, and let us continue our discussion on diamond turning machining. Last class we started this topic and we have seen that this particular process has wide application area in a optics fabrication and the different type of lens fabrication. And we have seen there are different classification of the diamond turning operation like a x, y, z axis, that means number of axis, degree of freedom, and then second one was the x, y and the r theta type of thing, and third one is the facing and the flying operation. So, let us further continue by further on discussion of different axes. Now, this is called x and z axis configuration. Now, how these things are different? Now, you can see here, if you consider a normal turning operation, what happens that you give both the things to the, now this is your cutting tool, right. So, what we do that for desktop cut, we are giving a movement in this direction. So, that is obviously same as our conventional turning operation, what you want to do. But when you want to do facing operation, for facing also what we do, we give our x direction in this part, right, because for both the axis x and z axis, mostly we give this both the motion to the tool only, not to the workpiece. Workpiece just rotates only, and depending on that rotation we create a features on the either on the cylindrical face surface or on the cylindrical surface. But here things are different. Now, you can see here that in z slide actually you are moving only z axis in this case, that means your tool is moving only in z axis, and for this tool whatever is this headstock, the whole headstock is moving in the x direction, correct. So, this is what is different than the conventional turning operation. Why this is required? Because many times whatever we will see some of the application, and we have seen also that fabrication of those mold, micro mold, at that time your machining was done here at this location. At that time your tool was not stationary, but tool was considered as a milling tool. So, it was rotating at a high RPM, then you do machining here, then you want to shift to this location, instead of a tool moving in this direction, your whole job was moving in this direction, right. So, that was happening, we will see that video again. So, at that time you can do cutting here. So, it is better to mount your whole workpiece or the headstock on a x axis. So, that your whole workpiece will move in a up and down motion, that is when we are looking from the top, and your job or your tool is moving in a z direction only. And other than that you can actually control the location, that where you want to do machining of a different shape on the workpiece, that can be also controlled if this freedom is given to the workpiece, not to the tool, right. So, it is a 2 axis with a T slides. Why it is called T slide? Because now you can see here that this particular tool is moving in this direction and your workpiece is moving in this direction. So, that is why it takes a shape of a T. So, now this is the T shape. So, this is called T slide, and it is most commonly used, because now if you take this shape, then any conventional or routine type of features you can create on the face surface. So, that is the advantage, right. The slides are arranged in T type configuration with headstock carrying spindle head moves along the x axis and the table carrying tool post moves along the z axis. That is what we have discussed, that we are not giving both the motion to the tool, that is x and z. Instead of that we are giving only z motion to the tool and x motion to the workpiece. So, that is called x and z axis DTM. Now, tool is mounted on a rotary table. Now, this is not xz, this is a r theta. Sorry, there was a mistake little bit. So, this is a r theta, this is a r theta axis. Now, these things are different. Now, you can see it here. Now, what is happening, that this is a rotary table, instead of moving in the x direction or the z direction, now we are giving a movement in this direction. So, what is the advantage of this? That suppose you want to create some features which is some concave surfaces or convex surfaces, then you can get this thing done very easily. Depending on the overhanging of this, what is the radius of rotation of this particular cutting tool in terms of r and theta, you can get those thing feature. Now, you can see this dash line for creating these particular features. If your machine is in x and z direction, that is the part, suppose this is the x and z, then what you have to do, suppose you want this object, right, then what you have to do, you have to give a very small amount of xz, 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 then only you can create a this type of feature. This thing is not visible by naked eye, but when you magnify it, you can get these features visible in a microscope. So, that is the problem. But if you follow this particular path, what is happening, your tool is actually sweeping the surface, right, it is not actually making this thing in a micro step or the nano step. So, when your tool is sweeping in this direction, it is very easy to create these features by x and z r theta configuration. So, let me show you that video, that how these things are feasible in r theta mode. Right. So, this is the r theta mode. Now, you can see this is the same rotary table here and your tool is located here, your workpiece is here and your tool is actually moving around the surface. So, that you can actually create some type of spherical shape here. So, depending on the radius of rotation of this particular cutting tool, you can get the same surface on a workpiece. So, now you can see it is rotating. So, this is more convenient than giving the micro stepping on a x and z axis. Correct. So, this is one of the applications of r theta axis. Similar way, what you can do, you can actually create a concave surfaces also. Now, you can see that your tool is located at this location and then you sweep it. Then what it will do, it will actually create some type of cavity instead of a formation of a spherical surface. So, that is also one of the ways. Right. So, tool is mounted on the rotary table, that is here, and component is mounted on the spindle. The best suited for machining component with a circular arc only. So, these are the concave, convex surfaces or spherical surface, you need only circular arc. So, depending on that arc, you can create a features on a component. So, profile accuracy obtainable on this machine is much superior than that of the interpolated arc generated by the XZ type of machine. So, here that is the big advantage, because ultimately suppose you want to avoid those particular form generation, then what you have to do, if you use X and Z axis much type of machine, then you have to apply some type of polishing process on the top, because those marks are many times visible by naked eye also. If the stepping interpolation is at a micro or bigger size, tens of micron, then it is visible. So, you need some polishing process and then you can remove those things. But if you use r theta things, then what is the advantage, that you can get rid of those particular things and you do not need any type of subsequent polishing or finishing process. So, how in terms of machine, how this thing is different, right. So, DTM differs from the standard machines in two ways for generating enhanced surface qualities. One is the degree of agreement between the program contour and the actual machine contour is very close. Now, what does it mean? That suppose you are actually machining a surface. Now, suppose you want to do a cutting of this particular surface, right. So, this is the surface and your cutting tool is at this location and doing a facing operation, you are rotating in this direction. So, when your tool is following this particular path, that path following is done by a part program, correct. So, how much is the accuracy of that particular part program? That means the what program you are giving and at which path your tool is moving. So, that particular agreement is very high here. So, sometimes it is in a less than 1 nanometer, sometimes it is in terms of 1 nanometer also. So, that is the advantage of using that. Whatever program you are giving, same way your tool will work. Why it is working? Because we have very highly sophisticated components on the diamond turning machine, so that those things will make this possible. So, that is the one thing, that whatever program you are giving, your machine itself, machine will work exactly on the program control, but your machine will not sacrifice the accuracy or the resolution of your part program. And the surface finish obtained on the machine surface is the optical grade. Optical grade, that means it is in terms of the lambda by 2, what is wavelength by 2, 10, something like that, what we can tell it. So, it is in nanometers surface roughness. So, that is the advantage of using this thing. And conventional turning operation or facing operation, getting those things, even if you use a CNC machine, getting those surfaces at a nanometer level or angstrom level, it is not possible, because the machine also needs some of the things which are not available on a conventional machine. Okay. So, extreme control is possible due to coordinated functions between the extremely smooth spindle, precise and accurate positioning of the workpiece and the tool. Because now suppose you want to follow one particular path, now this is the particular path you want to follow. Now, this is very skewed surface, now you want to do machining of that part. So, now first thing is required the very smooth motion of the spindle, because if you will get a some type of uneven or some type of fluctuated movement of the spindle or rotation of the spindle, this feature generation is very difficult. And precise and accurate positioning of the workpiece and tool. Now, you can see this surface, it is very difficult to, you cannot, because it is not a symmetric, axisymmetric surface is not there. So, most of the times what happens, that for creating this particular surface, you can actually use some type of cutting tool and then you scoop out this material, and for this particular surface you have to scoop out material from here, right. So, accurate positioning of the workpiece, that where you are positioning your workpiece with respect to tool, that will decide that how exactly you are making this particular component, right. So, it has a two different features and both features are different. This is a concave surface, this is a convex surface. So, how to get both the features on a machining on the workpiece surface, that will be decided by the how many axis controls you have and how precisely your workpiece, tool and the spindles are moving. So, use of well defined high quality and wear resistance cutting tool, that is why we use a diamond, because diamond is the hardest material. So, unless you use a ferrous material for a workpiece as a workpiece material, you can actually enhance this particular life. So, mostly you diamond turn tool and this particular process is more suitable for the non ferrous material. So, because it is a very high wear resistant, high quality, it can retain its shape for a longer time compared to other cutting materials. Due to all of this, the inaccuracy on the surface machine by DTM can be controlled to a sub-micron level. So, that is the surface, that means what are the figure level is the, suppose you want to create a concave surface, you can create a concave with a sub-micron level of figure accuracy. Roughness will be obviously in terms of the nanometer level or sub-nanometer level. What are the features required on the diamond turning operation? So, first thing is the machine base stiffness and the stability, because if you use a granite bed and if you see this most of the features are actually aligning with the machine construction what we have discussed in the micro machining, because there also we need a very high damping coefficient of material, then we need a very high stiffness on the structural loop, everything is required here also, because here requirement is even more stringent, because our depth of cut is in a ones of microns only, and in that case you can actually give more depth of cut in terms of tens of micron, but that is this particular process demands even more than what is required on the micro machining machine. So, here machine stability, stiffness, so most of the things are actually repeated compared to that similar to what we have discussed in the micro machining machine component. So, we are not going into more detail, but I am just listing out the what are the things available. So, stiffness is required. So, what parts components you are making, how they are connected with each other, that is important. Smooth spindle motion and its accuracy and repeatability. So, mostly we go with a aerostatic spindle here. Most of the diamond turning machines have aerostatic spindle, and that is why accuracy and repeatability is obviously achievable, that we have discussed already in the aerostatic spindle lecture. Smooth slide motion with a high accuracy and repeatability. Here what we do, hydrostatic is the slide way here, and we have seen the hydrostatic slide way can easily move without any more friction. So, friction directly depends on the what is the viscosity of the fluid which we are using. So, here it is hydrostatic slide way. So, it is similar to the aerostatic way, but you will not get any type of wear and the friction in the slide surface. So, it can smoothly move with a record accuracy and the repeatability. Servo performance and position accuracy, that we will see the what is fast tool servo and what is the slow tool servo, and how quickly and how exactly you are positioning your tool with respect to workpiece. So, that will decide that what are how these things will work in tandem, because if you see that any of this particular component is not working as per its requirement, then your whole efficiency of the machine will be actually calculated based on the worst performance of that component, not with the best one, because your whole thing is actually restricted, operation is restricted because of the some worst performance of one component. So, that is the thing, but here we are using a different type of motion with a fast tool servo and a slow tool servo, so that you can get a actual position accuracy. Vibration control you require, because we know that we want to create a surface with a nanometer or sub-nanometer accuracy, then you need a vibration isolation, so that no vibration will come through the floor from any of the machine or any other things to the machine. So, vibration whatever is coming from the machine, that will stay there, but you are using some type of very more suitable material here. So, vibration dampening will happen within the component. So, it will also not propagate from one component to other component. Temperature control is required, because we know that we are cutting optical material here, and optical materials are sometimes very susceptible to the temperature. And other than that, you are using also very highly sophisticated instrument with a sub-micron of accuracy. So, if you do not control the temperature, because of temperature variation, you will get a different micro expansion or nano expansion of the component, and that will actually create a problem in the positioning and the accuracy. Tool measurement system you require, because we know that everything depends on how your tool is sharp and what is the waviness and the different type of angles on the diamond cutting tool, and how long you are maintaining that thing, because it is not that after one operation you are changing the diamond cutting tool also. So, diamond cutting tool can be used for a many different type of components. So, you need a in process optical tool measurement system here, what is shown here at this location. So, this particular tool measurement system will give you a real time view of the cutting tool, that what is happening with the cutting tool when it is interacting with the surface. And once the operation is over, then it will capture the one image of this cutting tool, and you have already captured one image before you do the machining. So, then it will compare then how is the difference between the reference image and the actual image. If the tool wear is very high, then you can replace the tool. If it is not high, then you continue with the cutting tool. So, this particular optical based tool measurement system is also required here, so that you can monitor the status of the tool. Tool quality and accuracy, if everything is correct, but you are not using a right cutting tool, that means what is the waviness of the nose radius and what is the cutting edge radius and how other things are there on the cutting diamond tool, those things also play important role. So, if you see here the tool temperature control, vibrations and smooth motion of the different axes, motion of the spindle, stiffness of the structure, these all things we have discussed in the machine tool components of a micro machining center. Okay. So, first thing is the spindle system, what are the different components here. So, it is the aerostatic spindle we use here. So, that is the reason that you have a very high accuracy and the repeatability in a rotation. Workpiece positioning system, mostly it is a hydrostatic bearing with a linear motor and the linear scale, or the laser based positioning and the feedback systems are extensively used. So, here for movement you can use the hydrostatic or the linear with a linear motor, because we have seen advantage of linear motor also, because it is also on the magnet base, and you will exactly get the required accuracy in terms of a sub nanometer level. And linear scale is required here, because you want to actually measure the how much it is traveled on a surface, whether it is in x direction or the z direction. So, linear scale with a sub micron accuracy or resolution, that will make sure that you are getting the required result. Laser based positioning system, because sometimes if you use sometimes non contact position measuring system or feedback system, then it is more advantage instead of a contact type of things. So, that depends on how much customization you require and how much more sophistication you require on the machine, depending on you have to spend more cost and other things also. Machine support system, we have seen the epoxy granite base and vibration isolator, same thing we have discussed in the micro machining machine component. Tool measurement system, that is located here, and the machine control unit. So, machine control unit will give you a synchronized motion between the spindle and the cutting tool. So, we will see that some of the features you need a very fine synchronization between the degree of rotation of the cutting workpiece and the how much penetration of the work tool is done on the workpiece surface. This is the same slide. Now, classification of the finishing process. Now, there are two ways you can classify the finishing process. Why we are talking about finishing process here? Because diamond turning is also one of the finishing process, where you can get the surface finish less than 1 nanometer. So, that is why it is also considered as a shaping and finishing process, while the normal finishing process whatever we are using, lapping and some type of advanced finishing processes, they do not actually create shape, they will actually do finishing only. So, we classify this thing in terms of two categories. One is called soft loop finishing process. So, what is this soft loop? That mostly it is related to the lapping process. That means, abrasive particles are randomly dispersed on the surface, workpiece is located here, and this is the lap which will actually carry these particles. And how this thing is there, that difference is the cutting tool comes in contact with the surface at many locations. Now, if you see our turning operation, we are using a single point cutting tool. So, our location is only one point, but here what happens that we are using hundreds and thousands of abrasive particles. So, when you plunge this workpiece down, what happens then when it is going down, at that time many abrasive particles will create a contact with the workpiece surface. So, material removal will happen at a different place with a different magnitude, because we know that sometimes when you are pressing the particles, small particles will not indent more, but big particles will indent more. So, different location on the workpiece you will get a different material removal. So, that is the one of the characteristic of the soft loop finishing technique. Higher points on the workpiece surface are subjected to higher material removal rate. That means, this is the big particle suppose. So, this particle will remove more material compared to small particle, because its indentation depth is more. So, you will get a variable removal rate at a different location. So, how this thing, the two initially imperfect surfaces, tool and workpiece surface changes the workpiece surface two initially imperfect surfaces, tool and workpiece surfaces changes the workpiece surface into the high quality surface during the polishing. So, now you can see that, now suppose you have two surface, now this is the one surface, this is the workpiece surface, now it is very uneven, right, and you have some particles here. Now, let me create something like this. So, this is the very uneven surface, and this is the abrasive particles here. Right, these are the abrasive particles, and at the bottom portion you have a lap. So, this is the lap. Right. Now, you have both have relative motion. Now, this is moving in this direction, both direction, this is moving also in this both direction. So, as time passes, what happens, these two are the imperfect. Our objective is to create surface on the workpiece. So, this is the workpiece. So, when time passes, what happens, because of this random motion here, it will do removal of the material from here every location, because we know that whatever portion is at the smaller location, at this location it will remove first, right. Suppose this is the surface and you are continuously bombarding surface particles here, then this part will remove first, this much amount. So, after sometimes what happens, that your surface becomes, your workpiece surface become like this. So, this is your workpiece surface, because all the unevenness whatever was there here, that is removed by the abrasive particles here. So, initially two surfaces are imperfect, then when time passes, at that time those two things becomes a highly polished surface, and you can get the required surface finish on the workpiece surface. So, that is called the soft loop finishing, right. So, the process is controlled by load acting on the tool workpiece surface and the relative speed between these two. Now, that is very important, because now see everything depends on how much you are loading it. Suppose this is the workpiece and this is the abrasive particles which are located here, right, and this is the base material. So, now first thing, how much you are loading. Loading will decide that how much abrasive particles, suppose this is the abrasive particle and this is the workpiece. If loading is more, what will happen? This particle will enter more, and if loading is less, that time it will means indent less. So, this is called more loading, more N. So, this is the N force, normal force, and this one is the less L. Right. So, that will decide the indentation. Now, decide the speed, that how much speed is required. So, now speed is depend on the how much, which way you are moving this component, right. So, first thing is the indentation. Suppose your workpiece is indented here, this is your workpiece and this is indented here. Now, indentation is not the everything, because now you have to remove this much amount of material, right. This much, once it is indented, this much amount of material you have to remove. So, now you have relative motion in this direction, this. If it is moving in this direction, when it is moving, at that time this much amount of material will be removed, because now your workpiece will, tool will move in this direction. So, this much amount of material is removed. So, everything depends on two parameters. One is the load acting on that, how much is the normal force, and at what speed you are moving. So, relative speed between the abrasive particle and this part. Right. So, process is self-correcting, it is not necessary to ensure the high precision motion on the tool and the workpiece. Now, we know that abrasive particles are randomly oriented and randomly distributed. So, it is a self-correcting. So, after sometimes you make sure that your workpiece is getting finished. So, you do not require very highly precise motion, because you do not want to control the motion of each and every particles. That is what is happening in the normal diamond turning operation, where only single point is there, so that you have to move this thing very precisely, but that is not the case here. So, what is the hard loop polishing? So, diamond turning is a hard loop, because we are using a single point cutting tool here. So, only one point workpiece come into contact with the cutting tool, right. So, process which uses a single point are not self correcting, right. So, if you give more time, nothing is going to happen, because you are getting material removed from the single location only, not multiple location. So, they need the same accuracy on the guidance of the tool as it requires on the surface, right. So, whatever is the surface accuracy is required, suppose you require a concave shape, right. So, your tool should also move like a concave shape, right. So, it has to move like this only every time, then only it can generate this particular surface. In the polishing process, what happened, that there are multiple cutting points are there. So, you have to need one lap something similar to shape like this, and then you give a motion. So, you can easily get the surface polished or surface machine. Right. The roughness and shape accuracy of the generated surface depends on the rigidity of the machine. Now, how much is the conformation between the motion of the cutting tool and what is the feature accuracy required on the workpiece surface. So, everything depends on how much is the rigidity of the machine. Once you give a depth of cut of a 0.1 micron, then can it continue with a 0.1 micron or at all the machine surface or not. So, that will decide by this part. And diamond turning is a hard loop polishing process, and that is the reason that it requires a very high level of accurate and the rigid machine. So, these are the two different ways we can classify the machining operation of a diamond turning and the other way polishing processes. So, let me finish this lecture here. We will continue this topic in the next class. Thank you very much.